We've talked about heat capacity and how different materials get energy transferred to or from them from the environment, mostly is what we've been talking about. So, for example, we had an ice cube that was melting because we left it out on the counter. But of course, materials are going to transfer energy between themselves and other materials too. This is why you wear a hot pad when you take something out of the oven. It's because it's hot and you don't want it to transfer all of that heat energy to your hand and burn you. So, for example, when I'm cooking eggs, like if I'm hard boiling some eggs, then my usual practice, when I take the eggs out, I've got some eggs in my pan and they have some hot water. So this is all hot eggs and hot water. And it's a little below the boiling point because, I usually boil it and then I let it sit for about 9 minutes. So then I'm going to pour off the water and I'm still going to have some hot eggs. And I'm going to cool the eggs down by adding cold water to the eggs because I want them to stop cooking after a certain time so they don't get overdone. So when I first put these together, the water is cold and the eggs are hot. But if I wait for some amount of time, then they will equilibrate. And depending on how many eggs I have and how much water I put in, then sometime later, this is all going to be probably just somewhat warm. So maybe slightly warm if I had a lot of cold water, or maybe kind of warm if I didn't add very much water. But the point is that the eggs are cooler and the water is hotter than they were before. My formerly cold water is no longer cold. The other thing is that these are both the same temperature when they're done. And what happened in this was that the eggs transferred, the hot eggs, transferred some energy to the water. So if I think about the eggs as the system, then heat left the system. So I will say Q eggs is less than 0. And if I think of the water as the surroundings, then the water gained that energy. But the point is actually that these two are exactly the same. They just have opposite signs. All of the energy that the eggs gave off was transferred to the water, in an ideal situation anyway. And so these two values, the Q water and the Q eggs, are the same. They are just different by one sign. And so in order to make them equal, I have to make one of them negative. It does not matter which one you make negative when you're doing this kind of a math. So let's think about this in kind of a concrete way. And we're gonna just keep our numbers pretty limited for right now. So let's just say that the eggs gave off minus 2,500 joules, so 2.5 kilojoules. Then if that was true, then the water gained 2,500 joules. Okay, so all of that energy from the eggs was transferred into the water. So let's make some numbers in here and let's ask ourselves, what would be the new temperature if the water started, let's say it was tap water, So maybe 10 degrees. And let's say we also added 300 grams of water. I never measure it, of course, so these are just estimates. But we want to find out what the new temperature of the water is. I was missing a few words there. If it started at 10 degrees and there were 300 grams of the water. So let's look at how we would do this. For the water, we can see that Q is equal to Cp times M times delta T is our generic equation. And for the water, this is going to be plus 2,500 joules. This is liquid water, so the heat capacity of the liquid water would be 4.184 joules per mole degrees Celsius or Kelvin. The mass, that's actually joule per gram. The mass is 300 grams. And then our temperature, we know that delta T is really T final minus T initial. And T initial is 10 degrees Celsius. And all of that together is going to give us 2,500 joules, or these are going to be equal. So if I work these through, then I'm going to multiply these two together, and then I'm going to divide them into the 2,500. So if I do that, I'll get TF minus 10 degrees is equal to 1.99. So we are going to solve for the final temperature by solving for the T sub F. So I'm going to add 10, and this is also in degrees Celsius over here. So that means that my final temperature of the water is, I gave myself extra significant digits that I do not actually have. So it's going to be approximately 12 degrees Celsius. So in this scenario, probably I underestimated how much energy the eggs are giving off, but these are not in numbers that exist in books. I can't look up what the heat capacity of eggs are in a very convenient way. So we can see that the temperature of the water only increased by 2 degrees. And so when we look at real systems here, we're always going to have something like this happen. And in this case, the eggs would have decreased in temperature and would also have ended up being 12 degrees when we were done. So when we're looking at real scenarios, we often have two materials that start at different temperatures and then they're going to end up with the same temperature. This is called thermal equilibrium. It just means that two things are the same temperature. So if two things are in thermal equilibrium, it doesn't have to be two, it can be however many you have. This just means that they have the same temperature. So let's set up a slightly more involved problem where we actually won't know what the heat flow is for our two samples. So let's say that we have 250 grams of water, and this is liquid water, and it starts with an initial temperature of 80 degrees Celsius. And we know that liquid water has a heat capacity of 4.184 joules per gram degrees Celsius. So we're going to add to it a chunk of aluminum. And this chunk of aluminum is 382 grams. And its initial temperature, it's just been sitting on the lab bench, so its initial temperature is just 20 degrees Celsius. It's not as warm as the water is. And its heat capacity, if you look it up, is 24.4 joules per mole degrees Celsius. So we have to do a unit conversion here. I know you can do this already. So take time and do that unit conversion. Just convert the moles of aluminum to grams. We do this by dividing out the molecular weight, and we should get 0.904 joule per gram degrees Celsius for our heat capacity for the aluminum. So we're going to put these two together, and then we're going to wait. And sometime later, we know that these will both be the same temperature. So we've got our water, we've got our chunk of aluminum. They are at some final temperature, which we don't know what it is. So that's our question. What is the final temperature? What is our equilibrium temperature? So let's think about what's going to happen. The water is hotter than the aluminum, so our water is going to transfer some of its heat energy into the aluminum. So the Q water will be negative, and the Q aluminum will be positive, and these two will be equal with opposite signs. So that means that Q water, we can set this up, will be equal to minus Q aluminum. And again, you can put the negative sign on either side. It does not matter which one. It will work out the same either way. Okay, so let's take a look. If we were solving for Q water, this would be 4.184 joules per gram degrees Celsius. We had 250 grams of water. And our delta T is T final, which is the unknown, minus T initial, which is 80 degrees. And then the Q aluminum would be equal to 0.904 joule per gram degrees Celsius times 382 grams, and then T final minus T initial. And we said that its initial temperature was 20. So these two are the same number. This is one unknown. So we can use this equation right here, and we can take these two equations and set them equal to each other with that sign change. Don't forget the sign change, because otherwise they will not be equal, and your math will get really messed up. But we can put these together now. So this will be equal to minus 0.904. Oh, no unitless numbers. Okay, so don't be intimidated just because we've got two variable parts by themselves, right? And we've got subtraction in there. These guys are just a number, and these guys are just another number. So we can do algebra with this. So if you see where we're going, pause the video and try solving for T sub f. If you're still not really sure, then don't pause the video, just kind of keep on going. Okay, so when I multiplied these two together, I got 1046. My leftover units are joules per degree Celsius. And then my TF minus 80 degrees doesn't change. On the right-hand side, this is minus 345 joules per degree Celsius, still multiplied by TF minus 20. Now, we have to keep these guys inside the parentheses together, but we can divide out. And I'm dividing out the smaller number because I don't like fractions. It will turn out the same way regardless. So when I divide these two I get on the left-hand side minus 3.03 multiplied by TF minus 80 degrees. This is all just algebra, is equal to TF minus 20 degrees C. So because I have a number that's multiplied next to two numbers that are subtracted in parentheses, I can distribute this number to both of them. So I'm just going to multiply it out. Minus 3.03 TF, and then I have a negative times a negative, so my sign changes, and that's going to be 243. Notice my units canceled out here. That's why this number doesn't have units. But this one will have units, and this is also in degrees. So the right-hand side was not changed in this process, but now I can get my variables on one side by themselves. So I'm going to move them over to this side because I've got a positive. I don't want to deal with a negative. But again, if you don't have a problem with negatives, then they will divide out, and that's no problem. So I'm going to add my 20 to both sides so that I can get these guys to cancel out. And then I'm going to add 3.03 TFs to both sides. I don't have enough room there, so I'll put it over here. 3.03 TFs. And we're going to combine like materials. So 20 plus 243 is 263 degrees Celsius. And then I have 1 TF and 3.03 more, so that's 4.03 TF. And now I can just divide out the TF, or excuse me, the 4.03. So my final temperature would be 263 divided by 4.03, which is equal to 65 degrees Celsius. So when you do a calculation like this and you get a number, it's a very good idea to stop and look back at what you did and say, does this number make sense? 65 degrees C. So look back at what your system was. I had some water that was at 20 degrees, or excuse me, 80 degrees Celsius, and I had some aluminum that was at 20 degrees Celsius. So my aluminum increased in temperature, which is what I expect, and my water decreased in temperature, which is also what I expect. I also expect that the change in the aluminum will be much more significant than the change in the water because the heat capacity for the aluminum is much smaller than the heat capacity of the water. So yes, I think that our number here does make reasonable sense and that we probably have the correct answer. So these kind of calculations are ones that we would use if we were doing calorimetry. I'm not going to talk very much about calorimetry. I might make a separate video if you have questions about it from lab, but I generally figure that you're going to get plenty of that later on. So calorimetry is measuring heat flow. And we also can use this to determine reaction enthalpies. Heat capacities, and heats of phase change, of transition. So any of those enthalpies that we're talking about, if you actually want to measure them, you're probably going to be doing calorimetry. So we're going to talk a little bit more about how we deal with reaction enthalpies and doing these measurements in our next video. But for now, just focus on the kind of calculations that we're doing where we're transferring energy and measuring that energy or calculating that energy using our equations with our heat capacity. And if we need to, we can also use heats of transition if we have a phase change.